In our previous videos, we talked about the purpose and type of the testing. You know that testing is carried out to determine the structural behavior as well as the load capacity of structural element. We also mentioned about various types of testing that can be carried out in order to achieve those. You can do modeling and simulation using software. You can do analytical study, deriving equations from the first principle. You can also conduct experiment in the lab, or you can also conduct field tests on site. Depending on the situations as well as the resources available, such as expertise, funding, facilities, equipment, software, and etc., different type of testing is selected. Now we are extending our discussions with our previous topic related to the testing of a beam in structural lab. We are going to talk about the setup of the experimental tests as shown in this figure here. You see there are many equipments involved. All these need to be prepared, properly installed before you can carry out the test. You will need to produce the beam specimen in the laboratory, fabricate it in accordance to the standard procedures as per the practice in the industry. Prepare the steel reinforcement, prepare the formworks, cast the concrete, do some curings, remove the formworks, and then bring the test specimen to the test. You know concrete requires 28 days to be matured, and fabrications of the beam specimen consume times. You will need to procure the materials as well as prepare the materials. In order for you to have the specimen tested, you will need to properly plan the schedule. The entire process may take few months. 1 month for curing and waiting for the mature, probably another month for you to fabricate the specimen if you are producing the specimen in batches. Let's say now you have the beam specimen ready. You will require a testing frame here. This frame is used to hold the hydraulic cylinder, which later going to induce force onto the beam specimen. Normally we will have this frame separated from the support conditions of the specimen. The purpose here is to avoid any undesired displacement due to the force acting onto the specimen leads to any disturbance and movement to the supports of the specimen. This may influence the test result later. Before you conduct any testing, it is always a good practice of you to check the conditions of the connections of the testing frame. This includes the connections between the elements of the testing frame as well as the base of the testing frame. You also need to check the conditions of the support as well. Make sure all the bolts are properly tightened, as you do not intend to have any undesired movement of the support as well as the testing frame. You have the hydraulic cylinder here. This hydraulic cylinder is connected to the hydraulic pump. There are two types of hydraulic pump. This one is a manual pump. There is also electric pump where you induce the pressure to the hydraulic cylinder by pressing a button. Personally, I prefer the hydraulic pump because as I induce the pressure, I have a feeling in terms of the pressure. This allows me to properly adjust the rate of the pump and stop precisely at the intended pressure. This is the handle for the hydraulic pump. You press the handle down, you inject oil into the hydraulic cylinder, and the hydraulic cylinder compress the specimen. The purpose of the hydraulic cylinder is to induce force onto the specimen. You will require a load cell for you to measure the force caused by this hydraulic cylinder acting onto the beam specimen. This load cell is connected to the data logger here. Data logger will detect the pressure induced onto the load cell and display the loads being applied onto the specimen. Now, this kind of test setup is a typical 4-point test setup. It is very often used to test the beam. There will be reactions from both ends and point loads as distributed by this steel I-beam. We have one hydraulic cylinder. In order for us to create 2 point load here, we can use a steel I-beam here sitting onto the rockers. Make sure the hydraulic jack is positioned at the center of the steel I-beam, and make sure this steel I-beam is rigid enough in order to create 2 equal point loads acting onto the specimen. Normally we assume these 2 point loads here are equal if we place this properly in the right positions. Now, for us to test the beam specimen here, we need to know the purpose of the testing. Are we testing the flexural behavior of the beam, or are we testing the shear behavior of the beam? This will govern the locations of these 2 point loads. If we would like the load to be shear loads in dominant, we will put this point load to be as close as possible to the support, normally less than 1.5 effective depth of the beam. Now, if we want to test the flexural behavior of the beam, we will need to have the point load here to be further away from the support. For really nice flexural behavior, the distance from the support here should be at least 6 times the D, which is the effective depth of the beam. However, in most cases here, researchers would like to keep the specimen as small as possible so that it is easier to handle and it is cheaper to fabricate. Having the distance of 6 times the effective depth might not be applicable. Therefore, most researchers will try to make this as further away from the support as possible. This is to avoid the shear failure, and most likely flexural shear failure is expected. Of course, you can reduce the size of the beam here, as the distance here is dependent on the effective depth here. If you reduce the effective depth of the beam, it is still possible for you to test the full flexural behavior of the beam. Only that you will need to reduce significantly the size of the beam, which can be significantly deviate from the actual specimen. Although it is possible for you to reduce the size of the specimen, but you need to aware that if you choose to reduce the size of the specimen, theoretically the size of the aggregate as well as the size of the reinforcement bar should be reduced accordingly. However, the intended size of the reinforcement bar and the size of the aggregate may not be available in the market. Even though you are testing the specimen in the scale down size, it may not fully reflect the actual situation as well. These are some limitations in conducting testing with the reduced size of the member. And then we have rocker here. The rocker looks something like this. We have 2 steel plates. The lower plate have two reinforcement bar welded here, while the upper plate have a reinforcement bar welded together. The center reinforcement bar normally bigger. When the two plates are assembled together, you will expect free rotations between the two plates. This is a typical rocker. For this test setup here, we have 1, 2, 3 and 4 rockers. The plate must be flat so that it gives a distributed stress, causing no damage or concentrations of the stress onto the concrete that can fail the specimen before the actual failure of the specimen. If you look at this kind of test setup, the specimen is allowed for free bending. Some researchers choose to have one end to be roller support. They intend to simulate the actual simply supported conditions. This is provided that the roller support is really smooth, inducing no frictional force, which often it is quite difficult to have in a heavy structure lab. Based on my personal observation, even though we provide a roller support here, we are still unable to guarantee a frictionless surface contact. Therefore, it made no significant difference if you use a rocker as the support or a roller for the support. Now you have to make sure the support here is strong enough where it doesn't undergo any lateral deformations during testing, as this could influence your results. Any deformations here will lead to the difference reading in terms of the deflections as measured by the LVDT later. So before you start do any testing, tighten the bolts. Although personally I feel this one is not strong enough. If you worry this one is not strong enough, you can actually put an LVDT here to measure if there is any deformations during the testing. If you realize there is any deformations of this support, probably you have to redesign the test setup, as any movement in terms of the support here will lead to different readings in terms of the deflections of the beam later. Let's say you are testing a beam specimen which is very high capacity. You worry this testing frame here may not be able to support it. Some universities have the strain gauge in place. You can simply install the strain gauge to the data logger to observe the response of this strain gauge. As long as no symptoms of yielding of the testing frame, the testing frame should be okay. Another thing you need to know about the testing frame is that the induced load here will ultimately lead to deflections upward of the support beam of the testing frame. Again, these deformations cannot be too large, as significant deformation here might lead to undesired lateral movement of this hydraulic jack. If you are not sure, you can actually place an additional LVDT here to measure the deformations. As long as the displacement is less than 3 mm, it should be okay. In fact, all this should have already been considered by your lab before it is being used to test a specimen. Some have this test setup to be custom made. It is already in place in your heavy structure lab. You can go and search for their specifications. What will be the maximum capacity allowable for this kind of testing frame? Normally during the handing over of the heavy structure lab to the university, the supplier will conduct commissionings to the testing frame, prove that within certain load capacity it is functioning well, without any damage and within the allowable deformations. One more thing about the instrumentations. You need to check the capacity of the hydraulic cylinder as well as the capacity of the load cell. Let's say if you estimate the beam specimen to carry the loads 150 kN, now your hydraulic cylinder will have to be with higher capacity than 150. Same goes to the load cell. Now choosing the load cell is another issue. If the capacity of the beam is only 150, you should go for the load cell slightly higher than the capacity of the beam. Let's say 300 kN or probably 500 kN. Don't go for a big load cell that can give you 2000 kN. Later you might have the problem with the accuracy of the load cell. And then we have this LVDT. LVDT stands for Linear Variable Differential Transformer. It is used to measure the displacement. You know that when a test specimen is subjected to load, it is undergoing deflection. LVDT cannot be used to measure the deflection. It can only be used to measure one directional displacement. If you put several LVDTs together, by measuring the vertical displacement at different locations, assuming the support here has no vertical movement, now you can plot the deflection. Now the question is, where do you need to place the LVDT? Normally we will have one LVDT placed at the locations which is likely to have the maximum displacement, which in this case, under 4-point load test, the largest displacement will happen at the midspan. For a typical 4-point test setup, we can put another 2 LVDT directly under the 2-point load here. Let's say now you would like to test the shear loads. You put your point load closer to the support. Then your LVDT will be placed closer to the support, immediately below the point load. Next, you see a digital camera here, or you can place your handphone here in order to take photos to monitor the crack on the surface of the beam. Your beam setup here, if possible, to have a clear view from the front. And normally we will paint the surface of the beam with white paint in order for us to monitor the crack during the testing. Now you have hydraulic cylinder to apply the load cell to measure the load, steel I-beam to distribute the loads into 2-point loads. You have rockers as the support, and you have LVDT to measure the displacement, and also digital camera to snapshot photos during the testing. The LVDTs and the load cell are connected to the data logger. The data logger will record the data. You will press the hydraulic pump slowly. This induces pressure in the hydraulic cylinder. Hydraulic cylinder apply load onto the specimen. At certain intervals of the load, you will need to hold the pressure for at least 1 minute to have the stress distributed throughout the specimen, and then you monitor the crack and record the data. You will need a computer to monitor the response of the specimen at real time. Normally we monitor the readings given by the load cell and the readings given by this LVDT in order to observe the response of the specimen. By observing the response here, we can see when the loads given by the hydraulic jack reach the highest point. We do not know when the highest point achieved, so normally we will increase further the loads applied onto the specimen until we see the drop of the load capacity of the beam, and it can no longer go beyond that highest point. After the confirmations, the beam is considered failed. That's why we need the computer to monitor the response. This is about the test setup.